We've talked about continuity before. I've tried to demonstrate that reality would not be very continuous if, for example, I'm holding the lecture notes with section 3.5, with what we're going to talk about now, and all of a sudden these lecture notes transform into, say, a ukulele. I mean, what the hell happened? Obviously, you know, there's something called video editing, which I'm trying to do a lot to make this experience as best as possible for you, since I can't be in front of you in a lecture theater. So perhaps let's go back to the lecture material, get rid of the ukulele, and maybe if there are some requests I'll try to play. I don't know how to, but I could try. So let's try this as well. Yeah, pretty bad at this. Now, limits are crucial for defining and understanding whether a function is continuous. And on the other hand, if we know that the function is continuous, we actually know what the value of the limit. Now, to elaborate on that, let's define what a continuous function actually is. So we'll say that a function f of x is continuous and point x equals a if, and there are three essentially elements that need to be fulfilled, all of them, for a function to be continuous. Number one, the function needs to be defined at this point, meaning f of a exists. Number two is to do with the limits. So the limit must exist, the limit when x tends to a of f of x exists. And finally, the limit when x goes to a of f of x must equal f of a. So if you have a function, general function f of x at a given point, x equals a, if you want to know whether it's continuous, you check whether the function is defined at that point and whether that is a real value. You check whether the limit exists, and also you check that the limit equals the function at that value. If it qualifies on all three, it is a continuous function. If it fails on any of these, it is not a continuous function. There are plenty of examples of continuous functions, most of those that you've used so far. For example, polynomials or any combination of continuous functions tends to be continuous, provided that you avoid dividing by 0. On top of that, there is actually a very nice application of this property, because if you know that a function is continuous at a point, then calculating the limit is incredibly straightforward. All you have to do is to plug in the value and you will get the limit by definition. So this is something that we're going to use and explore once we look into functions of more than one variable, where checking whether the limit exists is incredibly complicated. But if we know that the function is continuous, then we can actually calculate it very nicely. What we need to do is use this and try to apply it to specific functions. Try to find out whether specific points on those functions are continuous. So you can check this in section 3.5.1 in the lecture notes, and I'm going to try to guide you through the process of how you would do it for any general function. So we'll come back to the functions we've already looked at, and I'm going to make up a slightly different f of x, just so it's not boring, but it serves the same purpose. So let's say that we're looking at this point, x equals a, and we want to see whether it is continuous. So the first thing is you look whether f of a exists. In this case, it does. It is defined. You could see it. In this case, it would be 0. It doesn't matter what the value is as long as it exists. Next, you check whether the limit exists. So for the limit to exist, it means that approaching it from the left and from the right, you get the same value, which in this case it's true. So you tick option 1, you tick number 2, and also you see that the value that the function tends to is the same as f of a. So in this case, this point is continuous. So let's say that we have something incredibly similar. In this case, at x equals a, the value of f of x, so in this case, let's call it g of x, so it's not confusing. The value is actually here. So to check whether the point x equals a is continuous, you check this checklist. So first of all, you'd see that for g of x, f or g of a actually exists. So this one is fulfilled. You check whether the limit exists. So the value that it tends to from the left and from the right actually is the same. In this case, it's 0. It does exist. The problem with this point is that the value of the limit, which in this case would be 0, is not the same as the value of the function at the point, which, I don't know, we'll just call it 2. So it means it does not fulfill all 3 criteria, which implies the point is not continuous.
That's correct.
So this is essentially the way that you try to go about if you want to check whether a function is or it is not continuous at a specific point. You need to fulfill all 3 of these criteria, and if one of them is not fulfilled, then it is not continuous. As you'll see in the lecture notes, there's also plenty of other examples of functions that are continuous. Trigonometric functions tend to be continuous, except at points where you're dividing by 0. For example, the composite tangent or cosecant, where you're dividing by either sine or cosine, and they get to 0. Having covered what a continuous function is and the role of limits in defining this in a very rigorous mathematical way, let's try to move on and learn how to solve limits analytically. And this means going through my own biased but hopefully useful list of how to solve limits, essentially by spending the least time possible.